All right, so the law of conservation of energy, this is exactly like all of the other conservation laws that you studied. Whether they were the ones from chemistry, remember in chemistry we had conservation of mass, and that was matter cannot be created or destroyed in a chemical reaction. We already had conservation of momentum. Momentum is not created or destroyed in a closed system. Momentum stays constant. And the conservation of energy is the same thing. So basically, energy, you guys, can't be created or destroyed. So we merely transform energy from one form of energy into another form of energy. But the total amount of energy in a system, it always remains constant. Now, this is actually not the first time that you've talked about the law of conservation of energy. In chemistry, this was a topic. Now, you may not remember that, right? But if you do remember it, then this is kind of review for you. So in chemistry, you talked about the different forms of like chemical energy and transforming the different forms of chemical energy back and forth. All right. What we're mainly going to focus on is mechanical energy. So let me give you a few examples. Oh, well, before I give you the examples, actually, let me give you the exception. So there is one exception to the law of conservation of energy. All right. You probably recognize this person, right? I'm hoping. That is Albert Einstein. And for anybody who only knows one equation, right, you probably know E equals mc squared. Now, what this equation shows, you guys, is that mass can be converted into energy, and energy can be converted into mass. So I can take energy and quote unquote lose it, right? Because I can convert energy into mass. And then I can take mass and quote unquote create energy by converting that mass into energy. This is what we use for nuclear energy, right? For fission, for fusion, this is how the sun works. So the sun gives off energy. All stars emit energy that's gained from the conversion of mass into energy through fusion. You guys probably talked about this in chemistry too, right? Yes, no, no. I'm seeing some puzzled looks. so, uh, in the old days, this is one of the things that we talked about in chemistry. But just so you know, for us, we're not talking about nuclear reactions, right? So we're going to stick with the energy can't be created or destroyed, right? Unless there's a nuclear reaction, which, we're not going to talk about that, right? So some examples of converting from one energy to another, like I could convert electrical energy into light energy, right? That's what your light bulbs do. I could convert the kinetic energy of moving water or the kinetic energy of moving air into electrical energy. That's what dams do. So the water runs through a turbine in a dam, turns it, which spins a magnet around a coil, and that creates electricity that's delivered to your house. This is the same concept. The wind spins this turbine, which rotates a magnet around a coil of wire, creates electricity, it's pumped to your house. So we could take like this mechanical energy, mechanical kinetic, and turn it into electricity. Uh, we could take chemical energy. This is a motor from a car. So I could take chemical energy from gasoline and convert that into kinetic energy that moves the car. But in all these cases, I'm just taking one form of energy, converting it into another form of energy. So does this make sense so far, you guys? Yeah? Okay. So now where we're going to focus like I said, we're going to focus on mechanical energy. And we talked about kinetic, and then we talked about potential. So we're going to focus on the conversion of kinetic energy to potential energy. So if there's no friction at all, the change in kinetic energy is equal to the change in potential energy. So however much kinetic I start with will be how much potential I end with, or vice versa. All right? So I want you guys to think about a swing. Now, when you're little and you're on a swing, you don't know how to pump your legs, right? You guys have probably been in this situation. So I have this kid, and this kid is sitting on the swing, or it's you sitting on the swing, right? And usually you have to have someone push you. Or what they'll do when you're really little, they can pull you back and pull you up and then let you go, right? Okay, so let's say that you're a little kid back in the day. You're on the swing, and you have someone pull you back. All right, so you have someone pull you all the way to here, and then they let you go. Now, when you're all the way back here, you're a certain height above the ground. What kind of energy do you have at that point when they're holding you above the ground? So anyone, what kind of energy do I have here? When I'm being held still above the ground, I have all, what kind? Okay, so it's not, I don't have like zero total energy. I do have zero kinetic, because remember, kinetic is energy due to motion. And potential, well, here, let's write down the equations again, just right here so we could see them. So kinetic energy is 1/2 mv squared. Energy due to motion, I have to have velocity. Potential energy is mass times gravity times height. So to have potential, I have to have some height above the ground. So here, when I'm pulled up, I'm all potential. Now I swing down, 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 and I hit my lowest point. Now at my lowest point, let's say I'm not above the ground, so my height would be 0. So at this lowest point, I'm all kinetic. And then that kinetic energy starts to be converted back into potential energy. And here's me on my swing. And when I reach, I go up, 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 and I start to lose kinetic and gain potential, which means I'm losing speed and gaining height. And so at this point, I'll be all potential energy again until I have the max amount of energy, and then I start falling. Then my potential energy is being converted into kinetic. So as I go down, I lose potential, I gain kinetic. I lose height, I gain speed. And then I just keep going back and forth, back and forth, back and forth. Now, if there was no friction, how long would I keep going back and forth, you guys? Anybody have any ideas?
Until you like stop.
Yeah, well, until you decide to stop, right? Until you put your feet down or something. So if there's no friction, you would just keep doing this forever.
But wouldn't gravity kind of pull you down a little bit?
So gravity's always pulling me down. I'm glad you made that point. So gravity is always pulling me down, right? So gravity is actually what's providing this potential energy. So we're studying gravitational potential. So the reason that we have this potential is because of gravity. So gravity is trying to pull me down, which is why as I go down, like let me back. I'm sorry. Let me step back. I'm stepping over my words. So I get pulled up, right? By my mom, dad, big brother, big sister, friend, whoever it is. So I get pulled up here. They're holding me, and then they let me go. When they let me go, because of gravity, gravity is going to make me accelerate towards the earth, right? And so that's why I lose potential and I gain speed. So I'm gaining kinetic. So gravity's pulling me down, 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 down. When I hit this bottom point, gravity is still going to be pulling me down, but now I have a lot of speed, right? So that speed is going to propel me up, but gravity is going to keep trying to pull me down. So gravity is going to slow me down, slow me down, slow me down, slow me down till I stop for one moment. And at that point, when I stop, I don't have any kinetic energy anymore. I have all potential energy. Then gravity's going to try to pull me back down again, and I'll start coming back the other way, right? So gravity will pull me this way. It's always pulling me down. So on the way down, it's speeding me up. On the way up, it's slowing me down. But if there's no friction, then I just keep converting between potential and kinetic, potential and kinetic. Does that make sense? Now, the reason why this might not, you might be saying, but like, I know this, I know that you do stop, right? In real life, you do stop. In real life, you stop because of what? It's the F word. Nobody knows?
Friction.
Yeah, friction. Thank you. So in real life, I stop because there's friction. So in real life, not all of my energy gets converted between kinetic and potential. In real life, some of my energy gets converted into something else because of friction. Does anybody remember what that something else is? When I have friction, I get energy converted into what kind of energy? I'll give you a hint, right? When you get cold, you make some friction. And I'm generating kinetic into what? Thermal energy, you guys. So friction always creates thermal energy. It always creates a conversion between whatever energy you have, whether it's electrical, whether it's kinetic, whatever it is. Friction always will take some of that energy and turn it into thermal energy. This is why, if you're not able to, but if you go up to the roller coasters at Great America, put your hand on the rail, they'll be hot after the roller coasters run on it. Think about your car. I know that there are explosions happening inside your car with the gasoline, right? But that's contained to a very small area where the pistons are. But when you drive your car for a long time and you put your hand on the hood, it's really hot, right? That's because of all of the friction, all of the moving parts in the engine. So in real life, with friction, some of the energy is converted to thermal energy. So is it lost? Is the energy quote unquote lost to us? And let me give you an example. So like the law of conservation of energy states that energy cannot be created or destroyed, right? So like, I don't know if your parents are like this, but my parents, I was a typical kid. So I would walk into a room, I would turn on a light. Walk into another room, turn on that light. Walk into another room, turn on that. I never turned any of them off, right? Maybe turn on the TV, walk away from it. And my parents, it would drive them absolutely insane. And they would come in and yell at me and say, you're wasting energy. Could I just say, hey, mom or dad, back off. Energy can't be created or destroyed. I'm not wasting anything, right? That wouldn't have been good for my health. I don't know about you guys, right? My parents would not have reacted well. So I was still spending their money, right? But we're both kind of right, just so you know. So energy can't be created or destroyed, but when you convert energy into thermal energy, we can't we can't use it for useful work anymore. Remember how we have that work energy theorem, where the change in energy is equal to the work done on an object. But with this thermal energy, we can't use it to do useful work. So at some point, you guys, in the life of the universe, uh, all of the energy will be converted into thermal energy that we can't use to do useful work, and at that point, um, you know, we won't exist. Don't worry, because that's like trillions of years into the future. All right, you won't be around anyway. So, so with no friction, all of the kinetic energy is converted into potential, and all of the potential energy is converted into kinetic. But if we actually do have friction, we have something called efficiency. You guys have probably heard that word before. So the efficiency of an engine, or the efficiency of an energy conversion process, what we do is we take the final amount of energy that we get out of a machine, of an engine, of an energy conversion, and we divide it by the energy that we started with. Now, just so you guys know, um, when I take a piece of coal and I burn it, and I use that energy, that stored chemical energy, when I use that to heat up water, to turn a turbine, to make electricity, to bring it to your house, only about 20% of the energy that I get from that coal actually gets converted into electricity delivered to your house to do useful work. So that process is only about 20% efficient. And then inside your house, you're losing even more. So the efficiency of your utilities and stuff is not 100%. So this is why we're trying to find other options than burning coal, because the vast majority of all the pollution and all that stuff that's created by burning coal isn't actually helping us. Well, none of the pollution is helping us, but uh, because it's such an inefficient process, we're creating a lot more pollution than otherwise. All right. So in real life, because there's always friction, efficiency is always less than 100%. We can't ever have a motor that's 100% efficient. Um, and if you search YouTube, or if you look online, you'll see these free energy machines. They're also known as perpetual motion machines. So these are machines that make energy. And the YouTube videos they always seem to say that it's the government or some other bad actors trying to get us hooked on, I don't know, coal, or to steal our money or something, right? If we could all just install these free energy machines, we'd be okay. Now, can there ever be anything like this machine? Can we ever have a machine that gives us more energy out than we put in? From everything that I've just told you, is this possible?
No.
Yeah, it's not. That's right. This is not possible. It is not possible to build a machine that creates energy. Okay? There's only one way that we can get energy without converting it from one form to another. And I already explained to you what that was. Our one exception, if we build a nuclear power plant, right? In a nuclear power plant, we're converting mass into energy. And you guys know that nuclear power plants have all kinds of other issues surrounding them, right? They have nuclear waste. Accidents could be very bad. If you guys have seen the movie Chernobyl, or the miniseries, whatever it was, they talk about it. So there's no way to get free energy, right? We can only get out what we put in, And in real life, we always get out less than what we put in. All right? And then just so you guys know, I think I did tell you this, the majority of your electricity actually does come from nuclear power. So when I was a kid, I grew up really close to Zion, and the Zion nuclear power plant provided like 95% of our power for this region. But now Zion is shut down. If you know where Zion is, Illinois Beach State Park. It's up by the border, kind of near Lake Michigan. And if you go by Zion, they cool most of their water in Lake Michigan. So it used to be one of our favorite spots to fish in the winter. There would be striped bass. The water would never freeze there. So anyway, okay, so let's do a few problems. I have 3 problems that I'd like to do just to show you how we're going to use this. So in this problem, I have a roller coaster car. And the roller coaster car is brought up to the top of a 202-foot hill. So I'm just going to kind of draw this out because I like drawing, right? So the height of this hill is 202 feet. That's 61.5 meters. Now that wasn't picked randomly. For those of you who've gone to Great America, this is the height of the Raging Bull. All right, so I'm getting pulled up to the top of the Raging Bull. Now the car and its occupants, they have a mass of 600 kilograms. So the roller coaster car, it's at the top here. It has a mass of 600. I want to know, how fast will it go at the bottom of the hill? Well, you guys, I know that at the beginning of this, it has all potential energy, right? So let's figure out the potential energy at the very beginning. So at the start. So at the start, potential energy, mass times gravity times height, right? So the mass of the car is 600. I guess we might as well use 9.8 for gravity. So we know that gravity is 9.8 meters per second squared. And the height is 61.5 meters. So like I said, at the beginning of this, all of the energy is potential, and I could calculate that out. I can't do that in my head. It's going to be like 370,000 is my guess and check. So I got it to be 361,620 on my calculator. Can someone confirm that with me? I think it's right because it's close to my guess and check. Okay. Mark said yeah. So if that's how much potential energy it had at the beginning, then that's how much kinetic energy it has to have at the end, right? Because all of that potential energy is going to be converted into kinetic. So if it had 361,620 joules of potential, it's going to have 361,620 joules of kinetic at the very bottom, right? And we know the equation. So at the start, this was the potential energy. At the end, it's going to be all kinetic energy, be 1/2 mv squared. And at the end, I know the kinetic energy is going to be 361,620 joules. Because all that potential, all of it's converted to kinetic. And then the mass is 600. And I need to solve for V. So I'm going to have to do some algebra. I could do the simple math first. 361,620 equals 300 times V squared. And then how do I get rid of this 300? It's being multiplied, so I need to I saw someone mouth the word divide. So those cancel. And I don't 3,000 or 361,620 divided by 300. It's going to be like 120. Oh, I was off by a factor of 10. I got 1,205.4. Did you guys get the same thing? Wait, does that make sense to me? That doesn't make sense to me. Oh yeah, it does make sense. All right. Is that right? Yeah. Okay. And then so that's the velocity squared, you guys. So I got to get rid of that squared, so I need to take square root. Those cancel, and the square root of that. Remember, if you're using your calculator on your phone, if you turn it sideways, it turns into a scientific calculator, right? So the square root button shows up. And when I hit that square root button, I get 34.7 meters per second. Now, to put that in numbers that we understand better, because we understand miles per hour better than meters per second, that would be 77.6 miles per hour. That's if there's no friction. So if there's no friction, then you're going just a tiny bit over 77 miles per hour when you hit the bottom of the hill for the Raging Bull. Now, just so you guys know, there is very little friction. You know, they work really hard to reduce friction on that roller coaster, mainly because, well, for a lot of reasons, but one of the big ones is they don't want the rails to heat too much, because that causes expansion and it could end up being bad, right? So you do hit the bottom at around 75 miles per hour. It's fairly efficient in real life. And then, you know, just as a sidetrack, I don't know if you've ever thought about this, but how is a roller coaster like a swing, like a child swing? So my guess is that most of you have ridden a roller coaster, right? I see some head shaking no. I see some saying yes. All right. Most of you, a lot of you have ridden a roller coaster. I don't know if most. I saw a lot of yes head shakes. So you guys, in a roller coaster, it's kind of like that situation where you're really little and you're getting pulled up to the top, right? So think about that swing. If you don't know how to pump your legs, and someone pulls you up to the top and then lets you go, what you do is you as you go down, you lose potential energy, right? And you gain kinetic energy. So at the very top, we said we were all potential. And then we hit this point. At this point, we're all kinetic. And then we go back up until we hit the same height. And at that point, we're all potential, right? And as we go up this way, we lose kinetic and we gain potential. And then we come back down, we lose potential, we gain kinetic. So we gain speed, then we lose speed, gain speed, lose speed. Like a roller coaster is the same thing. So if I have a roller coaster, there's only one place where I'm getting pulled up to the top, right? That's at the very top of the first hill. So at that very first hill, there's that chain, and you can hear it's like click, 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 right? Do you guys know what I'm talking about? That's the only place where you're getting pulled up. After that, you're literally coasting. That's why it's called a roller coaster. There's no motor, there's no engine, there's no other place where there's an assist. So we're literally coasting through the ride. And as I go down, I lose potential and gain kinetic. When I go back up, I lose kinetic and gain potential. And then as I go back down, I am losing potential energy, gaining kinetic energy. So on my way down, I'm gaining speed. On my way up, I'm losing speed, right? On my way down, I'm losing height. On my way back up, I'm gaining height. So you're switching between those two things. Now, the max energy, the maximum amount of energy is at the top of that very first hill, right? So in real life, I'm sure that you guys have looked at a roller coaster, even if you haven't ridden one. In real life, I could never make the second hill taller than the first hill. That would be bad, right? Because my max potential energy is at the very beginning. The most potential energy I could get is that same amount. If I tried to make the second hill taller to get to the top of it, I would need more potential energy, right? Can't happen. I can't get something for nothing. So I would go down, I would go up, I would hit that spot, and then I would just go back down. And then it would literally be like a swing. I would just be swinging inside of here, right? So the first hill is always the tallest. And you guys, the first hill is usually the tallest by a significant amount because of friction. We don't want this roller coaster car to get stuck anywhere, right? So let's do a second example. So I have a sledder, and my sledder is at the top of a 12-meter high hill. So this is like a 4-story hill. I don't know where the tallest hill around West Leiden is. Do you guys know? Anybody go sledding? No? The tallest hill by me is in Broadview, if you guys know where that is. Broadview has like a Target, a Home Depot. It's down 25th Street. It's not too far from you guys. And that hill it's pretty high. It's actually higher than 12 meters. All right. And so I have a hill that's 12 meters high, and then I have a sledder on here going down on their little saucer. Okay. I want to know, what will their velocity be at the bottom? Now notice I didn't give you mass. I didn't give you any of that stuff, right? I'm going to give you a kind of a new equation right now, you guys. So we know that the change in potential energy is going to be equal to the change in kinetic energy, right? And at the very top here, he's all potential. So potential energy is mass times gravity times we're looking at the change in potential energy, so it'll be the change in height. And then for kinetic energy, at the bottom, it'll be all kinetic. And so that'll be 1/2 the mass times the change in velocity squared, right? Now, do you see any of these variables that are going to cancel out? Maybe one that starts with an M? Do you see that we have mass on the left and mass on the right? Right? So those two are going to cancel. And that leaves me with gravity times the change in height is equal to 1/2 times the velocity squared. And if I solve this algebraically for velocity, you guys, the velocity at the bottom of the hill, the velocity that I gain, is going to be equal to the square root of 2 times gravity times the change in height. So you can put this on your equation sheet. You can use this, and this is assuming no friction. So when we do the problems, we'll be in pretend physics world, and we'll pretend there's no friction. Now, when you're sledding, depending on the conditions, like right now, it's not good. But just like a week ago, all of the snow on the sled hills, it was just ice, right? So there was very, very little friction. It was crazy. So the hills were running crazy fast, okay? Now, how fast would I be going if the hill was like all ice? I'm on my saucer. It's a good sled. How fast would I be going at the bottom? Well, I could use this equation right here. And my velocity at the bottom would be the square root of 2 times gravity, which is 9.8, times my change in height, which for here is 12. So I would just have to punch that in my calculator. 12 times 2 times 9.8, and then take the square root. I got it to be 15.3. Did you guys get the same? So you got the same. All right, good. And then just once again, just to show you how fast that is, that's pretty stinking fast for being on a sled. That's 34 miles per hour. So when we last time my son and I went out sledding, I actually only went down a few times because I'm like, I'm pretty old and this seems really dangerous for an old guy, right? Because 34 miles per hour doesn't seem like very fast in your car, but it's pretty fast when you're on a little tiny sled zooming down a hill. If you hit a tree, that would be really bad, right? So does this make sense so far? Yeah. And then just so you guys know, like if you ever watch downhill skiing in the Olympics or the World Cup or anything like that, those skiers get up, over 70 miles an hour sometimes. And it's actually why people die skiing. It can be very dangerous. Like, I don't know if you guys have watched the movie The Parent Trap with Lindsay Lohan. But the mom in that movie, she died in a skiing accident like 2 years ago. So yeah, it can be pretty bad. Now anyway, let's do our last example. So I take a baseball and I throw a baseball straight up in the air. All right. Now the baseball is going to leave my hand at 15 meters per second. And the baseball has a mass of 0.12 kilograms. I want to know how high it gets. So in this example, here's me. I throw my baseball. I'm throwing it pretty much straight up. And then it's going to come back down. Okay. Now when it leaves my hand, the velocity is 15. And you guys, for sure, on your tests and stuff, you don't have to draw pictures. Just drawing it because I like to. Now the mass of that ball is 0.12 kilograms. And what I want to know is how high did it get? So what was the height above the ground? Like at that point. Let me move this up. So how high did it get? Well, when it was in the person's hand, when it was in the player's hand, the kinetic energy, 1/2 mv squared, it was all kinetic. And then as it goes up, it loses kinetic, gains potential, loses speed, gains height until it hits this point. So we need to know what the kinetic energy at the beginning was to know what the potential energy at the top is. So let's calculate that out. It's 1/2 the mass, which is 0.12, times the velocity, 15, squared. We got to square the velocity. So 225 times 0.6. I think it's going to end up being like 13. That'll be my guess and check. I got 13.5. So I feel good about that answer. It was close to my guess and check. Did you guys get the same? Okay. So then if it had this much kinetic, when it left my hand, it's going to have that much potential at the top. So at the top, I know the potential energy is going to be 13.5, and the equation is mass times gravity times height. So the potential at the top, 13.5. The mass of the baseball, 0.12. Gravity is 9.8 times the height. So 0.12 times 9.8. I'm going to round that to 1.2 instead of writing down everything. Does that bother you guys? No? Okay. And a kilogram meter per second squared is a Newton. I'm just going to write that down. And then if I want to get rid of the 1.2, you have to divide both sides by it. And 13.5 divided by 1.2, it's going to be 11.25 meters. So about 35 feet. It's a pretty high throw. So if we look, you guys, if we look at the problems, I gotta go back. If you look at those last 4 problems, they're very similar to the ones that we just did. So like, I have a woman skiing down a hill, neglecting friction. How fast will she be traveling? This person starting from rest, they're sliding down. How fast will they be going at the bottom? So those problems are very, very similar to these.